Okay, we're back. Fingers crossed that this works. Midterm review, maybe we should go through it very quickly while we can. Jumping straight to it, all logistics, Sean has had a number of posts on ED, so you can get all information about exam logistics there. The plan here is to cover the technical material that's on the midterm. And so just get a few things out of the way. Coverage, what topics are we going to cover on the midterm? Everything we've covered in lecture so far except last lecture's discussion on reliability. Okay, so the ACTs, NACs, timeouts, that's not on the midterm. Everything else is. In general, the test is only going to assume that you know the material we've covered in lecture. Okay? So everything we've covered in lecture is fair game. We're not covering, if we've not covered it in lecture or discussion section, then we're not going to cover it on the midterm. To the extent that you're using the textbook, use it to clarify for extra information or to clarify concepts for yourself. But always treat what we've said in lecture as ground truth. So if there's something where the text differs from what we've said in lecture, what we've said in lecture is what you should assume for the midterm. Okay? In general, just a rule of thumb for you to know, there's nothing on the test that involves complicated math or very lengthy calculations. So if you find yourself going down that path, you're probably on the wrong track. Okay? So use that as a hint to yourself. Other general guidelines, you should understand how things work and the solutions and algorithms we've discussed in class, but also be prepared to kind of go beyond and apply them to contexts that we may not have covered in class. So, for example, we might say, consider an AS that is not following Gao-Rexford policies for BGP. How would such and such work? Okay, you should be expecting to do that. Or we could be taking a solution we've discussed in class and applying it in a scenario or context that you haven't seen before. So like, here's a very strange topology. You get this particular sequence of failures. What would happen to distance vector? Something like that. In general, we're not testing your ability to memorize stuff we've covered. We're testing whether you've understood how things work. So again, use that as a mental picture for if you feel like we're testing how many bits were in the IP header, that was probably not the goal of the question. So use that to check whether you're on track. In general, if you see something that looks unexpected, don't let this daunt you. You have learned all the pieces, the building blocks you need to reason through a problem. Okay? So in terms of format, I believe we've released a number of midterms from the prior years, so I hope you have a pretty good sense of what the style of the exam is. We're kind of following the same style. So you can expect a set of about 25 quick questions. They vary in level of difficulty, and then we have a set of these deep dive questions on specific topics. Okay. So pace yourself accordingly. Often, not always, questions would tend to get harder as you work your way down towards the end of a question. So if you find that you're getting stuck on something, maybe move on, come back to it later. Don't spend all of your time on that last question in the quick question set. What else? Attitude, don't panic if you don't know something. We aren't expecting anyone to get 100%. None of us did. None of the TAs. I got a few wrong myself. So, and this is despite having done this many times. So just know that that's kind of the expectation. Don't panic if there's one question you aren't getting. You're probably doing just fine. Again, be confident that you have learned all the things you need to know in lecture in order to solve a problem. So there is nothing in a problem that should require you to know something that was not covered in lecture. Okay. Stay calm, as always. You can reason through it, I have no doubt. So this review, and what is the plan? We're going to try and walk through half a semester's worth of material. And so clearly I'm not going to do a deep dive on any particular thing. What I am going to do is walk through all the topics, the concepts as well as the details, highlighting what it is I expect you to know for the midterm. As always, just because I didn't cover it in this review does not mean that you don't have to know it. But if I did cover it in this review, you probably definitely should know it for the midterm. Okay? I think of the way you should use this review is kind of as a checklist. It's maybe a half an hour to go through. So when you go through it, use it as a checklist of, I was supposed to know this. Do I know it? Yes or no? Go check if you don't know it and come back to it. That's at least how I find these midterm reviews to be somewhat useful. My plan for today's lecture is I'm going to summarize, I'm going to walk through the concepts, just highlighting what you need to know. I'm not going to explain, but I also have probably, if I just keep talking to myself, I have maybe 45 minutes, at most 1 hour worth of material. So I am expecting you stop me anytime you want to go into more detail on something. Repeating a concept, repeating the point I just stated, why did you say that? Any questions you have, stop me and we can go into it. With that, any questions on midterms before we get started? Okay, so let's start. Going very bottom up, we started this class with talking about links. Right? What you should know about links are the important properties of links. The bandwidth of a link, the propagation delay of a link, this notion of the bandwidth delay product of a link and what it represents, the capacity of the link. And from those, you should be able to calculate how long it takes for packets to get delivered or for data to get delivered from one point to another. You should know the components of that delay. Transmission delay, time to get bits on the wire, propagation delay, which is the time it takes to travel across the wire, as well as queuing delay and why we encounter queuing delay. Okay? You should also just be, without doing calculations, be comfortable with ideas like, oh, I give you more bandwidth. What happens to your delay? Or I give you a longer link that is higher propagation delay. What happens to your transfer time? What happens to application performance? Okay, so just be intuitively comfortable with these properties of a link. From links, we went to routers, and we said that routers interconnect links, or you can start to build this topology. And for the first few lectures, we talked about routers as this fairly black box concept. But then more recently, we jumped into actually what a router looks like internally. And in Rob's lecture, we went into great detail on the internals of this. This is also, as you review, one of the things I like about networking, it's also both the challenge of networking, is you kind of have to keep all the pieces in your head. Like many other subjects, when you go study them, you learn algorithm A, and then you forget all about it, and you can go learn algorithm B, and the two have nothing to do with each other. That's not the case for networking. Networking is more where you learn these pieces, but they're all going to fit together, almost like a puzzle, which is kind of fun. So test yourself on whether you understand how these pieces fit. Okay, so for example, if I took this IP router, we said the IP router forwards packets from an input port to an output port. You should now know what does that mean, forwarding a packet. So a packet comes in, it has a header and a payload. You also now know what that header looks like, right? So you can say, what happens on this line card? I have to be able to parse the packet. So remember all those version bits in the IP header. Then you can say, I have to decrement a TTL. And then you can ask yourself, why do we have a TTL? Oh, we have a TTL because of loops. Why do we have loops? Because routing is this distributed asynchronous process by which we compute forwarding tables. And so sometimes we can have loops while things are converging. That's why we have a TTL. Okay, so you get that. Then you update the checksum. Why do we have a checksum? Check that you know that. After you've done the TTL and checksum calculation, what do you do next? You do an IP lookup. What do you do the IP lookup on the destination IP address? How do you do it? You do it with longest prefix match. Why do you need longest prefix match? Because we are aggregating IP addresses. Why are we aggregating them? For scalability reasons. Okay? And so once you have that lookup, then you forward your packet out the outgoing port. Where did that forwarding table come from? That's where the control processor in this picture comes in, right? That's where we're running all of these routing algorithms. That tells you now that control plane processor, that's the control plane of this router. Everything else we talked about is the data plane. Okay? So you should be able to understand both the big picture, things like control plane, data plane, and reduce it down to how these individual pieces are actually working. So things you should know about routers. Route processors versus line cards, what's getting done at each, this notion of a control plane versus a data plane, the notion of a fast path versus a slow path, and what gets processed where. And in general, know that the biggest challenge when we talk about routers is that on this data plane, we need really, really high performance. Okay, so things like options, things like fragmentation, they're stressful to the data plane. Going on with our topology. So we had links and routers. Ultimately, we said the reason we have all of this is to connect end hosts. Okay, end hosts are where we run applications. End hosts want to communicate with each other. We went from there to saying that a fundamental challenge in networking is this question of how we do routing. We then spent many lectures, Murphy's lectures, on how the basic kind of fundamentals and concepts in routing and how routing is implemented. Okay, so we talked about this notion of valid routing state. You should be very comfortable with what that means. No dead ends, no loops for any given destination. Okay. Then Murphy moved on to this notion of, okay, we have valid routing state. But what does it mean to pick good paths? And so we went into this question of link costs and computing least cost paths. Okay. So this is starting to optimize for some notion of cost metric. We talked about what those cost metrics might be. If we tell you nothing, then assume the cost metric is 1. But otherwise, typically cost metrics are things like the latency of the link. Okay? So you're optimizing for something like latency. You should know that sometimes we achieve forwarding through these things other ways like default routes and static routes. Right? So static routes was when a network operator goes in and manually configures a route that says, for this destination, go out this port. Why do they do that? Because, for example, you need to know where your destination host is connected to the router. And we said destinations don't participate in routing. So how does a router know where the destination is? Because we put in a static route. Default routes, very convenient if a certain router has only one link or network has only one link to the rest of the network, then a default route is very convenient. It says anything that's left over, go out that link. Okay. So it's a convenient summarization. In all other cases, we run this routing algorithm or this routing protocol. Any questions? Yep? Yeah. Yeah, what was the fast path versus the slow path? This entire path on the router, where data packets come in, they get quickly processed and sent out the output port, we call that the fast path. This is usually implemented in hardware. And it'll do a very fixed set of functions like, parse the packet, update the TTL, checksum, do the IP lookup, send it out. This is all built in hardware. Hardware is very good at going very fast for very simple and limited set of functions. If you needed to do anything fancier to the packet, you would bump it up to the control plane processor, where you might process the packet for things like options, or you need to look more closely at the packet. That's one distinction between, from a performance standpoint, fast path and slow path. Typically, we implement the data plane or forwarding data packets on the fast path because we get lots of data packets. We implement routing algorithms and the routing protocols, so BGP, distance vector, link state, those run on the control processor because we aren't sending that many routing updates and control plane packets. And actually running a BGP computation or distance vector is more complex. Okay, so there's control plane versus data plane. And there's fast path versus slow path. The slow path typically runs on the control processor. This gets confusing sometimes for people. Anyone want me to repeat that? Right. Moving on. So routing algorithms within a domain. So we first started with this fairly, I would say, simple view of graphs and how you compute routes over graphs. And we talked about 3 different approaches to routing. One, distance vector, link state, and spanning tree protocol. You should be very, very familiar with how each of these work, down to the details of what updates get sent, how forwarding entries get computed, and so on. You should also, to the level that you can apply them in different topologies and different scenarios, all 3 of them. Okay, so let's walk through each one at a time. So distance vector, a distributed asynchronous protocol where every router is independently running this distance vector computation. The basic idea is that as a router, I'm going to tell all my neighbors about my least cost distance to every destination. And then likewise, I listen to what my neighbors tell me, and for every destination, I pick the least cost path, and then I remember the next hop or the neighbor on my way to that destination along that least cost path. Okay. You should know the components of this solution in detail, where we advertise routes, the logic or the rules for when you update your routes. So if you remember, Murphy said, if you hear about a destination you've not heard about before, put it in your table. If you hear a lower cost distance for a destination than what you currently have in your table, then update your entry. Or if you hear from your current next hop with a change in the distance, then always accept it because that next hop knows best. Okay. We also talked about periodic versus triggered updates. And then we talked about this challenge of convergence, which is when things change. Routing is very simple when there's nothing changing in the network. if you have links go up, down, link costs that change, destinations that arise, then everyone has to